2.1. Our objective this time is to represent relations and graph linear functions. A relation is any kind of mapping from an input to an output. We can do that with an ordered pair, we can do it with a table, we can do it with a graph, we can do it with a mapping diagram. All of these should look familiar. So we're given a relationship defined with some ordered pairs. We're asked to find the domain and range. If you recall, domain means input values, range means output. If a number shows up twice in the input or the output, we only list it once. For example, I'm looking at my outputs. I see a 1 and a 1 again. I'm only going to have to write that one time. If you notice, I rewrote the range from smallest to biggest. You don't have to do that. It's just easier to kind of organize your data that way sometimes. Part B says, represent the relation using a graph and a mapping diagram. So in order to use a graph, I have to plot those 5 points. And a mapping diagram means I have to draw a shape with the inputs in it, a shape with the outputs in it, and draw arrows pointing from input to output. If you remember from Algebra 1, if every input points to exactly one output, then this is a function. If you look at my mapping diagram, you can see that all of my inputs point to exactly one output. The fact that one of my outputs gets pointed to twice does not matter. This is still a function because every input goes to one output. So example 2 says tell whether the relation is a function. And to explain, looking at part A, it looks like every input points to exactly one output. So yes, this is a function. And for the explanation, you'd write out something to the lines of every input points to one output. Part B has a problem. One of the inputs points to 2 outputs. If that happens even one time, we say this is not a function. And for our explanation, we would just put that in words. We would say one of the inputs points to more than one output. That would be good enough. At this point, you can pause the video and try to guided practice on your own, or you can do those later. The vertical line test. Vertical line test says if you've got a graph of a relation and a vertical line only goes to the graph one time, no matter where I draw that vertical line, it can only go through one time at the most. It can also go through 0 times. If that happens, you've got a function. That means every input has only one output. If you look at this other graph, there's a lot of places where I can draw a straight up and down line that goes to the graph more than once. If you can do that even one time, it is not a function. So looking at a graph, it's real fast to tell whether or not something's a function. Go ahead and pause the video for a moment and read this and try to figure out what it's asking. What it comes down to is this problem is asking whether or not these relations are functions. I see a couple problems with the first graph. I can draw a vertical line in a couple of places that makes us see that the vertical line test fails. Therefore, this first one is not a function. Looking at the second one, I don't see anywhere that I can draw a vertical line and go through 2 points. So the second function, or the second relation, is a function. And for your explanation, you would just put into words how you know this is true. Talking about inputs and outputs in the vertical line test. At this point, you can pause the video and try this on your own, or you can continue on and do this later. Next up, we're going to be graphing equations. We've got 3 steps that we do when we're graphing something for the first time and we don't really know any of the shortcuts. We construct a table of values. When I say that, I mean we'll do something like x, y, and then plug in some numbers. Doesn't really matter what numbers necessarily. We're going to plot points from that table until we see a pattern, and then we're going to connect the points with a line or a curve. To start off, we're going to graph what's called a linear equation. It's called linear because the highest exponent is 1. This is going to be a straight line anytime the highest exponent is 1. You might remember how to graph a straight line using slope and y-intercept from Algebra 1. We'll focus on that a little later in the chapter. Right now we're just going to make a table. The easiest number to put in a table is normally 0. And my recommendation is always do some points a little bit bigger and smaller than your easiest number. Since this is just a straight line, I'll use 3 points total. And we plug those numbers in and get 3 outputs. Once we've got those outputs, we plot these points on a graph, and hopefully we can see a pattern. Again, this is a straight line, so the pattern should be easy to find right away. I made a slight error on my table. I had a positive 3 there before. The reason I caught my error is I ended up with a third point up here, and I knew that didn't look right when I tried plotting 1, 3. At this point, I do see a pattern. I can draw a line straight through those points, and I've got my graph. Next, we're going to decide whether a function is linear. Remember, linear means the highest exponent is 1. First one we can see already, we've got an exponent that's 2, so this is not linear. And then we're asked to evaluate the function when x equals -4. Second one, we can see that the highest exponent is 1, so this is linear. And there's a couple ways we can evaluate f of -4. We could just plug the number in, and we'll get an answer. I prefer to use synthetic substitution, where I write my -4 and set up the coefficients. I see my first coefficient is -1. My next coefficient is -2 and 7. Drop my -1. -4 times -1 is 4. -2 plus 4 is 2. -4 times 2 is -8. 7 and -8 make -1. And I get my answer right away. Notice when I use my synthetic substitution, the biggest number I see in the entire problem is -8. Whereas regular substitution, I had a -16. I have to deal with bigger numbers. It's personal preference. You can do it either way you want. Overall, I'm pretty sure that you might agree that synthetic substitution is easier. Drop the 5. -4 times 5 is -20. Add them. Done. At this point, you can pause the video and try the guided practice on your own, or you can do these later. Our last example, we'll go ahead and pause the video, read what's going on, and we'll discuss it shortly. Now we're going to try to graph this. We might have our x-axis be the depth and the y-axis be the pressure. We need to come up with a good range of values. Our depth is obviously going to never be negative, so the smallest depth we might want to use is 0. The biggest depth that we'll go to, you can see in the problem, is 130 feet. So our inputs could be anywhere from 0 to 130. To figure out our good range for our pressure, we can just plug those numbers in. Plug 0 into our equation, and we get 1.03. Plug in 130 and we get 4.9. Those might be hard numbers to put on our graph, so it might make more sense to do something like this. And we can draw a graph that uses that scale. This also gives us a couple of points we can plot. Plug in 0, we got something really close to 1, so I can plot that point. Plugged in 130, we got something really close to 5, so I can plot that point. Since this is a linear equation, I can just draw a line to connect. Now it's asking us what the pressure is at 33 feet. So 30 is going to be here, 33 would be a little further. Looks like our pressure is somewhere real close to 2. In order to figure out exactly where it's at, we can just figure out what P of 33 is. Put that into a calculator and we'll see that we get 1.99 atmospheres to use the correct unit. And that's it for this lesson.